Now moving into our next presentation, we have Paul Witherell with us on enabling better communication with AM standards. Paul Witherell is a mechanical engineer in the process engineering group of the Systems Integration Division of the Engineering Laboratory at the National Institute of Standards and Technology. His primary objectives at NIST are to develop and transfer knowledge to industries, including knowledge about information models, additive manufacturing, and system-level analysis. Research efforts aim to leverage engineering and information sciences to benefit design flexibility, cost and cycle times in additive manufacturing. Welcome, Paul. Thank you for joining us.
Perfect. Thank you. Thank you again for having me, and hello all. So yeah, thank you for the introduction. I'm going to talk a little bit about some enabling better communication with AM standards. Let me just going to turn on my pointer here too. So a little bit of background. Thank you for the introduction again. From the National Institute of Standards and Technology, NIST. It's a national lab under the U.S. Department of Commerce. We have 2 locations in Gaithersburg, Maryland, and in Boulder, Colorado. So I'm actually from an engineering lab there where we focus a lot on the processing technologies in additive manufacturing. But it's really a multiple lab effort in additive manufacturing there at NIST. A lot of the work that we do is in measurement science, we call it. So we're looking to develop a technical basis for standards. So we do some fundamental science and fundamental research that looks to develop some technical underpinnings for standards that we see recognized in some of the stuff that the folks just talked about. The folks at NIST, we don't actually develop standards at NIST, but we do serve on standards committees. We're very active in the ASTM community. We're very active in the ISO community, the ASME community, and the SAE community, to name a few. Again, those are just specifically additive manufacturing technologies. And really what we see our role is in the coordination, the facilitation, and the communication roles. So a little bit about my particular background. So in the engineering lab at NIST, we have kind of a breadth of some of the activities that we are involved in developing the measurement science. We're very active in the process side of things. We primarily focus on metals additive manufacturing in the engineering lab. We do a lot of research on powder bed fusion and studying the process. We do quite a bit of research in studying part qualification and process qualification, and also work in the materials qualification for additive manufacturing parts. My background is actually more on the data science side of things, the informatics, and the work that I've been doing, I guess for the past 6 or 7 years now, is looking at how we represent information and how we use information and how we leverage information in additive manufacturing. So I'm going to talk a little bit about the communication aspects of that today. So a little bit of the overview. I'll talk a little about AM production. So when I talk about communication, I'm really talking about moving past the rapid prototyping into the development and creation of parts, which is essentially where we're at today, and we've heard from a lot of our presentations. I'll talk a little bit about the global supply chain in additive manufacturing very briefly. I'll touch on today's unique circumstances with COVID-19, the coronavirus, and some of the opportunities and challenges that it's created. And then finally, I'll go into the role of standards, and I'll talk about several standards that are in development and well underway in additive manufacturing that really facilitate the communication about part processes and about the parts. So as I think we've heard quite a bit of today, and we'll continue to hear throughout to tomorrow during this marathon, is we've moved past prototyping for additive manufacturing. We're leaps and bounds past where we were 10 years ago. As I mentioned, I'm focused in the engineering lab is really on the metal side of things. But it was only a few years ago, maybe 2, 3, I guess maybe 4 years ago now, we used to talk about the GE fuel nozzle and how we were having additive manufacturing parts that are now in production. And that's really moved. That needle has moved quite a bit in the past few years. We've moved beyond some non-critical parts in the aerospace energy industry into parts across industries being developed. We've looked at it as supply chain. We've looked at it for the development of unique designs that you can't really create with any other processes. So here's kind of a sample of some of the parts that we are now being realized using additive manufacturing technologies. As I mentioned, we see from the aerospace industry, we see from the automobile industry, we see from the medical industry, and of course the defense industry as well. And when I first created this slide a few months back, maybe a year ago, I was really surprised to see this one, as I wasn't familiar with at the time. But the amount that additive technologies have really been applied to reduce part production, part numbers, and just increase our production capabilities and our production flexibilities. But what we are seeing is when we are creating these accepted parts, they're often specific to the machine, to the material, and to the part build configuration. So we're finding things that work, and we're trying to kind of dial it into that thing that works. And so the result of that is, with current AM production, our supply chains are more vertical. And this is something that people will discuss. And as we've moved and we've matured into production of AM parts, what we are seeing is folks are working with what they're comfortable with. They're working with the folks who are who they've trained, who they've worked with quite a bit. They're purchasing different companies to help with their production. They're dedicating resources towards specific parts. This is across organizations, across agencies, and across industry. Even within the organizations and creating these vertical supply chains, you're seeing continuous engagement between the design and the manufacturer of the part. It's not as streamlined as it is in perhaps more traditional manufacturing processes like machining, of course, because of the intricacies of the additive manufacturing process. There's still a lot of uncertainties that people are trying to deal with. But we are seeing that there's often a lot of back and forth in trying to get a part up into production. And once it is in production and suitable parameters are sort of found, the process and the parameters in design traditionally are usually locked down when something's found. And so now the question is, as we acknowledge that we have a little bit of a vertical supply chain, and people are talking about and wondering how they can make some of these additive manufacturing supply chains more horizontal, particularly with the DoDs, different agencies, and larger industries as well. And of course, the small industries looking to get more involved in the supply chain. And so what we're seeing today with the current environment, what's happening is that there actually has put some unique circumstances on our global supply chains through the COVID-19 response. We're seeing people trying to get more access to different types of medical equipment, to prevention and response equipment, and to parts for that equipment. So we're seeing a lot of demand there in the traditional supply chains. We're seeing companies like GM moving over some of their production facilities to help with the response for the COVID-19. But we're also seeing a lot of the response in the additive manufacturing 3D printing community, and we've heard quite a bit about that over the past day. So the COVID-19 has created a bit of unique events and a unique opportunity to assess the readiness level of the AM as part of the global supply chain. So when we start thinking about it, we start looking, and folks are looking to create AM parts for different equipment, to replace ventilator valves. We're starting to see, that we're seeing an opportunity for AM to really step up, and we're seeing people step up at various levels, going from the hobbyists to the production facilities. I know quite a few hobbyists myself, folks that are developing some of these face masks that are, bringing them to hospitals and helping with the protective shields to hold them on their face. But we also see in Italy where they've actually used 3D printing, additive manufacturing to develop to valves to extend the life of some of these ventilators and how they're being applied. So as I mentioned, the circumstances is really creating an opportunity for what we do in additive manufacturing and 3D printing. And across the supply chain, it's given 3D printing a little bit of a new visibility, if you would, and additive manufacturing new visibility, and some of the implications that can have across the global supply chain. So one of the things that I guess I'll be talking about for the rest of this talk is, what are the consequences of doing it with additive manufacturing as opposed to a traditional manufacturing process, an injection molding process, a machining process, or a stamping process. And so we've heard a lot about this, the complex geometries, these unique shapes that we can create. They actually can create challenges on how we're able to communicate geometry, the types of geometry that communicate, and how we want to communicate the geometry. The complex processes where it's, we don't have these design allowables that we see in some of these more traditional processes where we can correlate a material with a certain set of process parameters and say, okay, if you use this material and you process it in this way, this is what you're going to get for your final part. We know that the processes are a bit more complex than that, and create some challenges in how you communicate about the parts that you want to develop in additive manufacturing. And of course, that goes all the way into the inspection side of things. The complex testing and inspection, whether it's SEM, TEM, XCT, or some type of optical surface measurements. We're seeing some very stringent testing requirements on additive manufacturing parts because we're not really sure about, we know we have uncertainty in the process, and we want to measure it as much as possible to make sure that the part that we're creating is actually the part that we wanted. So all of these are actually creating some unique challenges in how we communicate across from the designer to the manufacturer to the inspector. It really goes into, how we communicate across the suppliers and communicate with our own organization. These create some unique data and model requirements. And of course, that, as I mentioned, that those requirements, they go past just looking at creating a part and communicating some unique geometry, but it also goes into creating the designer communicating with the manufacturer. If you design for additive manufacturing, where there's specific design considerations that somebody made that they want to communicate with the manufacturer, or how the manufacturer communicates back with the designer to say what the limitations are on the design that they created. And of course, this also goes all the way into inspection when you want to do some certification or the qualification. And the idea is when you design for an intent, you design against some certain requirements. If you're using something complex, as we start to see more and more lattice structure usage, and we start to get into functionally graded materials, how do you really qualify against something like that? What do we have that can help us qualify against that? How do we specify those requirements, and how do we show that we've actually met those requirements? And so those are some of the challenges that we're facing that are unique when we see these unique process capabilities of additive manufacturing. What are some of the unique communication challenges that we have as we want to communicate between suppliers, within organizations, and across organizations? So standards in additive manufacturing. We heard a little bit about standards from the last presentation. I'm pretty sure we're going to hear a bit more tomorrow. Among other things, documenting best practices. We do quite a bit of that underlying work at NIST, looking at design rules, design guidelines, and testing as well. Define test methods and protocols. Accelerating the adoption of new technologies. Specifying requirements, communicating guidance, and documenting technical data. And so these last three are really where I'm going to focus for the remainder of this presentation is the idea of specifying requirements, communicating guidance, and documenting technical data, and communicating, just the communication amongst people. My screen seems to have frozen right there. Hold on one second.
If you stop share and share again, it might work as well.
All right, we moved. Thanks. Consensus product definition and data package standards. So these are three particular efforts that I'm going to talk a little about today. Most of my goal is to familiarize people with these efforts. Maybe some of you are facing some of these challenges. Maybe some of you are anticipating some of these challenges. Maybe many of you are already aware of some of these efforts. So my goal is to really educate some of the activities and some of the research that's being done to help and facilitate this communication. Some things I want to point out before I jump into these efforts is that not all scenarios require AM-specific considerations. So I talked about some of the uniqueness that we can do when developing additive manufacturing parts. That doesn't mean you necessarily have to go to these specific extremes. Sometimes it just takes a simple document or a simple communication. Sometimes you don't need to identify AM-specific requirements, and sometimes it's as simple as using what's already available. But sometimes you're using something a little more specific. So those scenarios that do benefit from AM-specific considerations are not often or not always one size fit all. And so these are some of the considerations that we make in these different efforts. Voluntary standards can and should underpin stakeholder-specific requirements. So the efforts that I'm going to talk about today are underway under ASME International and under ASTM International and ISO. And so these three different efforts are actually all looking at standardizing different aspects of how we communicate additive manufacturing requirements between the designer, the manufacturer, and the inspector. And also all three of these are consensus voluntary standards efforts. So these are being developed within organizations that are allowing for the voluntary adoption of the standards. And so by creating standards and looking at communication this way, it makes something that's more open to adoption across the globe, across the community. And it's not looking at saying thou shalt do it in this particular way, but more, it's driving, it's community-based, consensus-based driven. So quick couple of slides about the product definition for additive manufacturing. So what we talked about, and this is an effort that actually started about maybe 6 years ago, and we're talking about product definition in additive manufacturing. We're looking at what we usually consider with geometric dimension and tolerancing, GD&T. And we look at what the tolerances are on traditional designs. These tolerances have traditionally been applied in drawings. When we look at how you specify something, these are usually done when you communicate these drawings and pass these drawings. And so when somebody takes them to manufacture, they look at the tolerances and try to manufacture something within the tolerance. Additive manufacturing creates a couple unique challenges for the GD&T community. One is, and it's still difficult for us to transition between the drawings to the final, to the model-based enterprise and model-based engineering. The idea that we're transferring as additive, as it states in this marathon, is a digital process. So it does require some sort of digital representation before we create these parts. And so even if there are drawings of a part that you want to create additively manufactured, at some point you're going to have to switch over to the model. So this is something that we took into consideration a few years back. Here's a couple of examples of some of these complex geometries. And as I mentioned, it's been a challenge within the community. This has been developing under the Y14 community. It has been a challenge to move past from the symbolism more to the representation. And so, when you see these annotations on a document, this is more human consumable, human readable. And what we're trying to do, and we're challenging ourselves to do, is communicate some of these unique geometries that we can develop in additive manufacturing that we might not be able to create in other types of processes. But another challenge with additive manufacturing is when you want to communicate a little bit about some of the process considerations that you may have made. So traditionally, when we talk about GD&T and product definition, we want to focus purely on the geometry. But there are exceptions to the rule when we think about castings and forgings, and we think about composites and the implications of the manufacturing process on the final part and the final part requirements. And so what we've done in the 14.46 community and the Y14.46 is not only start to consider and make unique considerations for how we want to communicate some of these unique geometries, but also how we might want to communicate some of the unique process requirements. So this particular document was initiated in May 2015 under ASME. So that makes it about 5 years old this month, next month. Sorry, I spelled June wrong. It'll be going to ballot again in June 2020. We've actually just completed in the past few months a 1 year of we call it a draft standard. And so this standard's been out to the community, to the additive manufacturing community, to the general community for the past year and a half. And the thought was to get some feedback from folks as far as where this hits, where this misses, and what are some of the things and some of the communication challenges that folks still have. We had some good feedback from that year and a half. We put it through one more ballot a couple months ago. I didn't pass that ballot. We still have a few comments that we have to address. But this particular standard is really in its final stages. By no means is it a mature document as far as where the community is. There's plenty of room for advancement and improvement, but it really it provides a starting place for this communication and having these discussions between folks, between the designer and the manufacturer. and finally onto the inspection, which hits a little bit more on this next effort. So that first effort that I talked about under ASME, that's the idea of, again, the GD&T under the context of product definition. The idea that we have some unique process requirements and some unique geometry requirements that we may want to specify, and how do we do that through our model-based enterprise and through our models, really. The second effort right here is actually under the different community. So this is not under development under ASME, but is in development under ASTM International and ISO, the International Organization for Standardization. And this effort is a little bit different as we're focused on the data packages for AM parts. So this one actually gets a little more into the weeds, a little more into the details, a little bit more into the additive manufacturing requirements, the specifics, and the idea, and we heard a little bit about in the last presentation about different levels of criticality, different levels of complexity, different levels of capability as well. And so when we start to think about what type of information we want to communicate between folks, how do we package that information? How do we structure that information? How do we pass that information? So this particular effort was driven by, we talked a little about qualification and certification. This particular effort was driven by approaching these folks from NADCAP and saying, what are some things that would help you do your job better? And the idea was, there needs some more data-specific standards for the qualification and certification of parts. What do those data packages look like? For those who are familiar with perhaps the US DoD, the idea of a technical data package, or what does that information boxed up look like that's going to show that this part that you created is the part that we asked for. This effort it's a global effort. It's got folks in input from the ASTM community and the ISO community. So from ASTM International, it's got a heavy on the US side of things, but still representation from different countries. And of course, we're well represented on the ISO side of things too, where different countries, they do have a stake in the development of this particular standard, and they have voting rights. And so the idea is that we come to not only consensus within the ASTM community, but within the ISO community. I think you'll probably hear more tomorrow about this unique agreement between ASTM and ISO, but this particular standard actually falls under both organizations. So it will be developed as an ASTM standard and then also be recognized as an ISO standard moving forward. So I talked a little bit about some of the, what are we talking about, the details of additive manufacturing, some of these details and some of the information that we might want to communicate. So some of the I mentioned at NIST, we do a lot of this underlying science, underpinning measurement science and fundamentals. So one of the things that we looked at from the data side is we looked at the data flow, moving from this raw design to a final qualified tested part. And we got really into these activity diagrams, and we decomposed the activity diagrams to really look at the information flow across these different functions, across these different processes. And what it allowed us to do was to create really an explicit, packages of information associated with different sub-activities within the process to help us understand what level of control we might have potentially capable of when we want to communicate between not only from the design and the manufacturer, but also from design to the inspector. So when we looked at some of these use cases, and again, we talked a little bit about the capability and criticality, but also the idea of different use cases. And so, some of these cases, in the supply chain, we might have the acquisition, we might have the manufacturer in-house, we might have the verification only. So depending on what the use case is, maybe we already have production in place, we only want to look at the verification of a particular part, versus maybe we want to send an acquisition out to somebody who we are just starting these preliminary expeditionary developmental process runs with. And so one of the things that this particular standard is looking at doing is looking at these different use cases that we might want to communicate between different folks, what that level of detail is between this communication and what that information that should be associated with those types of communication. And again, the idea is to try to be more explicit in how we communicate between different organizations at different levels of need, going from all the way from low capability to high capability. And we are starting to take some security considerations into this as well. It's by no means the cybersecurity standard, but the idea is, in communications, effectively with the global communications, the idea of cybersecurity and understanding that there are implications in how we communicate this information. There are considerations that need to be made. So I'm going to touch on this one last effort that really just started up in this past, it's been ongoing, I guess, for a year and a half, but it's really actually just started as an actual standard effort in the past month. And this is development of a common data dictionary. And this effort is really focusing on, so the first one talked a little bit about the GD&T aspects and the product definition. The second one really focused on the data packages and how you want to communicate between the different organizations, different criticalities, different levels of need. And this third one, Common Data Dictionary, is really looking at the idea of having some well understood common terminology. So the objective of the CDD is really to kind of provide well understood basis for how you communicate between different types of information. This particular one is really focused on the metal side at this stage as well. But as we look at different levels of the hierarchy, there are different. It does a starting point for other processes as well, or other materials as well too. And so what the CDD activity is doing is looking to standardize some of the terminology that is used to how we exchange reference and how we exchange data. And what this will help us do is when we start to look at materials qualification, materials development, part qualification, and then even into data analytics, federated databases. And so it becomes a little more detailed in how we exchange the information, but that fine-grain control really allows us and exposes us to a lot more opportunities and what we can do with some of the shared information. So as I mentioned, this effort was actually been ongoing for about a year and a half now. It's been coordinated by NIST, but it's recently actually become an effort that's under a new subcommittee under ASTM F4208 on data for additive manufacturing. And it's a new work item that was just initiated under there. So the recap that we have, I guess I've touched on a couple of times. The ASME standard is looking at the GD&T and the product definition. And under ASTM and the ISO organizations, we have one that's being developed under data packages and looking at how you share requirements. And finally, the Common Data Dictionary and looking at the sharing of key terminology and key terms. And together with all these, we're literally looking at different aspects of the communication requirements. But the idea is these standards, and as we develop these standards, then we move to something that's actually accepted. There's something that folks can then use. So none of these are actually passed yet. The closest one is the ASME one. But the things that the folks actually use to have common understanding, common terminology about how you communicate between different organizations and between different levels within your own organization. So sorry, I guess I have a couple minutes for questions, but thank you.
Thank you, Paul. We have a few minutes left. We can get through a few questions. Top question for you. What are the top 3 areas that need to be standardized in additive manufacturing?
I mean, so that's an easy one and a hard one all at once, right? And so ideally, we could standardize the processes and how we communicate the processes. So imagine having one type of build process perimeter type thing that we could send to any type of machine that would know how to create the part. But of course, different manufacturers all use their own settings, with all use different technologies, and so that's very difficult to do. Standardized materials, the idea that you have the materials that you know what your materials are going to do. But of course, that's a little bit of a challenge too. And how do we measure those materials? How do we qualify these materials? And maybe standardized data communication, I think, is just as important as all those other ones. And that helps us kind of standardize how we interpret what their inspection criteria are, what their qualification criteria are, what the certification criteria are.
Awesome. I think we have time for one more. So how can we make such a complex qualification process more simple and easy?
That's also a great question. I think a lot of people are starting to ask the question themselves as well, because I think one of the things that we've seen in additive manufacturing is because of the uncertainty with the process, we've gone into some very complex testing procedures to try to qualify things. We saw a little bit about the XCT and identifying porosity in the XCT of different parts, but just because we find the porosity doesn't necessarily mean that the part can't be qualified, because we don't necessarily know what that porosity does to the actual performance of the part. And so I think more and more people are starting to look at modeling and simulation, ICME approaches, and look at different ways to actually understand, when we find a variation or we find some sort of defect, what the implications are. And I think that will help us understand a little bit more about what the thresholding is for when we should care about potential defect and when we shouldn't.
Thank you so much for joining us today, Paul.
Well, thank you.
Thank you.